When we hear the term black hole, our minds might conjure images of a cosmic vacuum cleaner, an empty void sucking in everything nearby. But let's dismantle that common misconception right from the start. A black hole isn't a hole in the traditional sense, like a puncture in the fabric of space. It's not an emptiness. Instead, imagine the most extreme concentration of matter, a point where an incredible amount of mass is squeezed into an infinitesimally small volume. Think of a star many times more massive than our own sun, crushed down to a space smaller than a city, or even a pinhead. This incredible density is the key to its power. What defines a black hole, then, is not absence, but an overwhelming presence. Specifically, an overwhelming gravitational presence. It's a region in space-time where gravity has become so astronomically intense that it overwhelms all other forces. The gravitational pull generated by this super-compressed matter is so formidable, so relentless, that nothing, absolutely nothing, can escape its grasp once it crosses a certain boundary. Not a spaceship, not a planet, not even the fastest thing in the universe. Light itself. This is what makes them black. They absorb all light that hits them and reflect none. The concept hinges on something called escape velocity, the speed needed to break free from a gravitational field. For Earth, it's about 11.2 kilometers per second. For a black hole, the escape velocity within its critical boundary exceeds 299,792 kilometers per second, the speed of light. Since nothing can travel faster than light, according to Einstein's special relativity, once light enters this region, it's trapped forever. So it's less of a hole and more of a cosmic prison, forged from the most potent gravity imaginable, a testament to the universe's ability to create objects of truly mind-boggling density and power. Imagine approaching one of these cosmic behemoths. As you get closer, the gravitational pull intensifies, but there's a specific, invisible boundary you might unwittingly cross. This boundary is known as the event horizon, and it's a term that carries profound implications. It's not a physical surface you could touch or see, like the edge of a cliff. Instead, it's a theoretical demarcation in space-time, a one-way membrane surrounding the black hole's central singularity. Think of it as the ultimate cosmic checkpoint beyond which all paths lead inward. The event horizon is defined as the point around a black hole where the gravitational pull becomes so strong that the escape velocity equals the speed of light. Inside this boundary, the universe is, in a sense, flowing inward faster than light can flow outward. So if light, the universe's ultimate speedster, cannot escape from within the event horizon, then nothing else we know of can either. It's the ultimate point of no return. Any object, any information, any glimmer of light that crosses this threshold is irretrievably lost to the outside universe, captured by the black hole's immense gravity. What happens if you were to cross it? From your perspective, you might not immediately notice anything dramatic, assuming you weren't torn apart by tidal forces, which is a story for another time. But for an outside observer, watching you approach the event horizon, your image would appear to slow down, redshift, and eventually freeze at the boundary, never quite crossing, as the light-carrying information about you struggles increasingly against the gravitational pull. The event horizon is a true frontier, marking the edge of the observable universe from the black hole's perspective, a place where our understanding of physics is stretched to its very limits and beyond. Chapter 3. One of the most mind-bending aspects of black holes, and indeed of massive objects in general, is their effect on the passage of time. This isn't science fiction, it's a direct consequence of Albert Einstein's theory of general relativity. Einstein taught us that gravity isn't just a force pulling objects together, it's a curvature or warping of the fabric of space-time itself, caused by mass and energy. And just as a bowling ball warps a trampoline, a massive object like a black hole creates an incredibly deep well in space-time. Time, being an integral part of this fabric, is also affected. The stronger the gravitational field, the slower time flows relative to a region with weaker gravity. This phenomenon is known as gravitational time dilation. So if you were to hover near the event horizon of a black hole, a feat requiring immense energy of course, time for you would pass much more slowly than for someone far away, say, back on Earth. While minutes might tick by for you, years, decades, or even centuries could be passing for the rest of the universe. It's a cosmic fountain of youth, but with a rather perilous catch: the proximity to an all-consuming gravitational abyss. Imagine two twins, one stays safely on Earth, while the other orbits a supermassive black hole just outside its event horizon for a short period of their own time. When the adventurous twin returns to Earth, they would find their siblings significantly older, perhaps even long gone. This isn't just a theoretical curiosity. Gravitational time dilation is a real, measurable effect. Our GPS satellites, for instance, have to account for both special relativistic time dilation, due to their speed, and general relativistic time dilation, due to being in a weaker gravitational field than us on the surface, to function accurately. Near a black hole, these effects are amplified to an almost unimaginable degree. Chapter 4. Black holes aren't primordial objects that have always existed. The most common type, stellar mass black holes, are born from the death of colossal stars. Imagine a star far more massive than our Sun, perhaps 20 times its mass or even greater. Throughout its life, this stellar giant is a battleground between two immense forces. Deep within its core, nuclear fusion, the process of lighter elements combining to form heavier ones, generates tremendous outward pressure and radiation, pushing against the star's own immense gravity, which is relentlessly trying to crush it inward. For millions or even billions of years, these forces are in a delicate, fiery equilibrium. But all stars, no matter how massive, eventually run out of fuel for their nuclear furnaces. For a truly massive star, this exhaustion triggers a catastrophic series of events. When the fusion in its core can no longer produce enough outward pressure to counteract the crushing inward pull of gravity, the star begins to collapse under its own colossal weight. This collapse happens incredibly rapidly in a matter of seconds. The outer layers of the star rebound off the now super-dense core, exploding outwards in one of the universe's most spectacular events, a supernova. This explosion can outshine an entire galaxy for a brief period, scattering heavy elements forged in the star's heart across space. While the outer layers are blasted away, the fate of the star's core depends on its mass. If the remnant core is still massive enough, typically more than about 3 times the mass of our Sun, no known force in the universe can halt its continued collapse. Gravity reigns supreme and unopposed. The core continues to shrink, crushing itself down past the density of an atomic nucleus, past any state of matter we can replicate on Earth, until it theoretically becomes a point of infinite density and zero volume, a singularity. Surrounding this singularity, the event horizon forms, and a new black hole is born from the ashes of a dead star, a silent, dark monument to an epic cosmic demise. Chapter 5. Just as planets and stars rotate, black holes can also spin. In fact, it's believed that most, if not all, black holes in the universe are spinning, some at truly incredible speeds approaching the theoretical maximum allowed by physics. This spin isn't just a trivial characteristic. It profoundly alters the black hole's properties and its influence on the surrounding spacetime. These rotating black holes are known as Kerr black holes, named after the mathematician Roy Kerr, who first solved Einstein's field equations for a rotating uncharged mass. The spin originates from the angular momentum of the progenitor star that collapsed to form it, or from matter it subsequently accretes. A spinning black hole doesn't just have an event horizon, it also possesses another fascinating region called the ergosphere. This is an ellipsoidal, or squashed sphere-like region located outside the event horizon. Within the ergosphere, spacetime itself is dragged around by the black hole's rotation, a phenomenon known as frame dragging, or the lens-thirring effect. Imagine a whirlpool. Even if you try to stand still in the swirling water, you'll be carried along. Similarly, within the ergosphere, it's impossible for any object to remain stationary relative to a distant observer. It must move in the direction of the black hole's spin, like a cosmic tornado sweeping everything with it. This frame-dragging effect is so powerful that it could, in theory, be exploited. The Penrose process, a thought experiment, suggests that energy could be extracted from a spinning black hole by sending an object into the ergosphere and having it split into 2 pieces, with one piece falling into the black hole and the other escaping with more energy than the original object had. The spin of a black hole, therefore, isn't just a passive property. It makes the black hole an even more dynamic and complex entity, warping and twisting the very fabric of reality around it, influencing the motion of nearby stars and gas, and potentially powering some of the most energetic phenomena in the universe, like quasars. And there you have it, our first 5 mind-altering glimpses into the bizarre and captivating world of black holes. From understanding that they're not empty voids, but regions of unimaginable density, to the chilling finality of the event horizon, the strange warping of time in their presence, their cataclysmic births from dying stars, and the cosmic dance of their spin, it's clear that black holes are far more than just curiosities. They are fundamental components of our universe, shaping galaxies and challenging our deepest theories about the nature of reality. This is just the beginning of our journey. We've only scratched the surface of these cosmic mysteries. There's so much more to explore, so many more layers to peel back. If these first few facts have ignited your curiosity, and you're enjoying this deep dive into the cosmos, please do show your support by giving this video a like. It truly helps us continue to bring these explorations to you, and I'm genuinely curious, which of these first 5 facts resonated with you the most, or perhaps blew your mind the widest? Drop your favorite fact in the comments below. I'd love to read your thoughts and start a conversation. The universe is a vast and wondrous place, and sharing its marvels makes the journey all the more rewarding. If you know fellow space enthusiasts, aspiring astrophysicists, or anyone who simply loves to ponder the big questions, please share this video with them. Stay tuned for part 2, where we'll delve into even more astonishing truths about these gravitational titans. Until then, keep looking up, keep wondering, and never stop exploring the magnificent cosmos we inhabit. Thank you for joining me, Alexander Bringadal, on this adventure.